Hi, everybody. My name is Ricardo Oliveira. I'm the CTO co-founder of ThousandEyes, and I'm here to talk about internet intelligence. So this is part of a product effort we have been undergoing over a bit over a year now. So about a year ago, we released a capability called Internet Outage Detection, which showed up in a product in a very subtle way. So it was more contextual information on path visualization. So over the last year, we've been working on a full-fledged feature set where you're able to see outage events and other interesting things, micro-scale events that are happening in the internet on a dedicated portal. And it's going to be almost like a product on itself. And that's what I'm going to talk about now. But first, just to clarify what we, ThousandEyes, what we think is internet intelligence. So when we talk about internet intelligence, what exactly is that, right? So the way we think about it is mainly the mapping of dependencies between users, applications, and the internet infrastructure under it. So it's almost like the connection between these two worlds. So there's the infrastructure world, you have service providers, CDNs, CNS providers, infrastructure as a service, hosting, and then you have the other world, users accessing applications, more and more SaaS applications, obviously, and more applications going through the internet. Also, part of the intelligence is the detection of large-scale events. So we're not necessarily interested in a user having issues with a laptop or an access point going down or even a branch office or connected to a data center having issues. So we're talking about here large-scale events at service providers at the core of network. For example, a router in AT&T, a core router goes down, affecting potentially millions of users. So that's, or someone decide to leak a route belonging to Amazon, and suddenly nobody can do shopping online. So those are the types of events we're interested here. Another component of internet intelligence is performance benchmarking. This is more relevant if you're interested in planning your service providers, if you want to know about comparing different service providers in different regions. There should be data you can use to help you through that. So why do we need all this data? Obviously, there's more and more use cases and applications that rely on the internet, software as a service, hybrid one. You have people working from home, connecting to the VPN endpoint in the data center. You have mobile workers. So all these cases rely on the internet. And obviously, once you move from a network you control to a network you don't control, is the best effort service, right? So there's unknown performance. There's, you lose control of things. The other thing is the existing solutions. So if you think about traditional monitoring solutions, and this was already covered before, so the way they work is mostly through packet flow capture for the most part, or device polling, which works well if you just interested in what's going on within the four walls of your environment. But once the traffic goes outside of that environment, then they won't help you that much. And so that's where this type of data can help you. So just to talk a little bit about the data we collect. So there's two main types of data. There's agent-based data in the form mostly of path traces in this case, which are our version of traceroute. And right now we have close to 7,000 agent instances between enterprise and cloud agents. We have about 150 agent locations, so that world map over there represents the locations where we have cloud agents. And then on the other type of data set we have, so the first data set is mostly active probing, so it's sample data. Second data set is routing tables from routers in mostly tier 1, tier 2 networks, so big carriers. We have been using data from RouteView, so they're one of our partners. And we have about 600 routers across 200 autonomous systems. And this data is not, it's not sampled across the prefix space because we get all the routes. The only sampling that happens here, obviously, is on the other end because we cannot access every router in the internet. We only have access to 600, right?
So did you say you were using RouteView's data then?
Yes.
Okay. That's a reasonably good footprint.
Yes, and they've been increasing footprint over. I mean, they've been around since the 90s.
Oh,
actually.
yeah. Yep.
So
University of Oregon, I think.
I did my entire PhD based on them, actually.
Nice.
So I only have good things to say about them.
Yep.
All right, so a question rises is how much of the agent data, how much of the internet we cover with the agent data, right? Okay, we have 150 locations, we have thousands of agents, but what does that really mean, right? How much are we covering with all those agents? So we tried to get some sense of that. So what we did here was basically to map each agent to a BGP prefix. So an agent is installed inside the network, reachable through a BGP prefix. We map the prefix to an autonomous system it originates. And so we look at all the routing tables from those 600 routers and see how those routers are reaching each agent. And then if the agent is inside ASP A, for example, we assume ASP A is covered. And if the agent is if the A is using a provider that B, for example, is directly connected to another service provider, we also assume that provider is covered. So we're talking about the one hop radius around the agent, basically. That's our notion of coverage here. And then how we classify an ISP. So an ISP in this case is an autonomous system that has 10 or more customer networks or other autonomous systems as customers. So we use a relationship inference algorithm to determine the relationships between autonomous systems, and then we filter out every ISP that has less than 10 customers because those are more in the border of the network. So if you look at an eyeball, for example, so two different cases, an enterprise ASN, like our case, ThousandEyes, we have an AS number. You can see from, probably not from this laptop, but in my laptop I have a sticker with the AS number. I don't know why. It won't be included here because we don't provide service to anyone. Google won't probably also be included here because it's mostly an eyeball, so they pair with a bunch of other networks, but they don't provide transit, right? So these mostly like big carriers. If you distribute all these autonomous systems, there's about 1,500 of them as service providers at this scale. You see that we have pretty good coverage in North America region. And by the way, the world map, the way we did that is mapping the ISP to the HQ where the ISP is. So it's an approximation for big networks, obviously. It's not very accurate, but it gives a sense of coverage. So in North America, you have a pretty decent coverage, 78%. If you look at Asia Pacific, APNIC is also 61%, close to that, so it's also pretty good. Once you start talking about Europe, which is ripe area there, then you start seeing lower numbers. And the reason is because it's a very segmented market in Europe. So there's a lot of countries. Each country has its own national provider. So you need a lot of agents to cover all those service providers.
I've just one question for that. If you would, let's say, get your information from all the internet exchanges in Europe, you covered the top 3, you have nearly covered all, let's say, 90% of the peering in Europe, yeah?
If we have an agent there in the ISPs, in the exchange points, yes.
Yeah. They are public available, so you could leverage that one. So I think if you cover AM6, D6, and the London one, you have the majority of the peering that is ongoing there, yeah?
I think there's a route views instance in at least one of those already, right?
Yeah, this is the agent coverage, but yeah, the route views they have on the exchange points have presence, yes.
Oh right, okay, yeah.
We still probably be missing the tier ones because they only do private peering, the big carriers, but you would coverage a bunch of folks that do public peering in the exchange points. So talking about tier ones, a good segue. So this is another way to look at the data. So what we did here is from that set of 1,500 ISPs, let's pick only the tier ones. What's a tier one? Is a service provider that do not only provides transit or peer with other networks. So they don't buy transit from any other network to exchange traffic. And there's about 25-ish in the world in different regions. So in this graph, you can see x-axis tier ones, y-axis number of agent locations where we actually have an agent inside that tier one network. So there's a huge concentration, a big concentration across North America. So most of those tier one service providers on the left-hand side, They're headquartered in North America. And then once you start looking at the right-hand side, see a bunch of zeros there. Those are mostly tier ones that are European-based. So KPN Netherlands, Orange France, Sparkle is Telecom Italia, Telefonica Spain. So we have coverage gap in Europe, basically. But for the most part of North America and some parts of Asia, in terms of tier one coverage, I think it's pretty good. This is yet another way to look at the coverage. So what we did basically is pick one big network, in this case Cogent, and we look at the world map they have available in their homepage, and we compare with the locations that we cover from the past traces that we sent from all the agents. So how many of their POPs we cover, right? So if you look, there's a big overlap there in terms of coverage. I would say it's probably a bit over 60%, just because there's cases like this where you have our agent covering this point, and there's collocated points there, and our geolocation, it's not accurate enough to distinguish those two locations. But this is just another way to look at coverage. Obviously, this doesn't scale to do this study across all the networks. It's pretty hard to do, because you need grand truths for all the networks you want to look at. All right, so what does all this mean in terms of product capabilities and how we're commercializing all this data? So basically, there's a beta program that's going to start soon. We're going to have a portal dedicated to visualize internet outages. So it's an event stream. You'd be able to configure alerts on outages. And what type of outages are we talking about? Mostly traffic outages that we detect from past traces, or routing outages from the BGP data, right? And again, these outages have a certain magnitude or scale, so we're not talking about micro outages, data center level, or branch office. These are macro scale events that impact users as well. It might impact users in a branch office, but that's part of the context we're providing is also the notion of population of users impacted or test impacted. So this is just to give you an idea how we do the outage detection for the traffic case. So the way we do this is superimposing all the data from all the customers, all the past traces, from all the agents we have in the system to all the applications we have configured. We superimpose that over time, and we start looking for patterns of packet loss. So in this case, you have two customers. Customer one using a New York agent, customer two in Boston and Los Angeles agents. And then they use different applications, but you see they all converge in level 3, San Jose, and there's a performance degradation there. So this is, I like to say this is similar to what's going on with Google Maps. You look at Google Maps, you see the streets with traffic, because people open Google Maps and they're stuck in traffic, and they feed that data back to Google. So this is a similar concept here, the crowdsourcing, right? Obviously, there's a lot of work that we did in terms of filtering all these events, lots of noise going on out there. So we don't look at what's going on in the edge. We exclude firewalls and load balancers and all that stuff. We only look at service provider networks. We also filter events over time. So if an interface is always losing packets, it gets excluded from the outage because it becomes the baseline. And at the end, we have a more curated set of events that we show in the interface. And this is what we currently show as a context. So you see in the background our familiar path visualization. In this case, it was an outage in Telia. So it affected 36 of our tests. And so you have all that context, number of locations, 5 locations, and more than 100 interfaces impacted. And the other interesting thing is once you mouse over the interface with red, which is where all the packets are being dropped, then you can also get some context around, okay, is this the only test being impacted, or is this a test that is an interface that is impacted a huge population of customers, right? Is it almost like that analogy, you're at your home and suddenly the lights goes off and you don't know if it's your switchboard or the entire block goes out. So this gives you an idea about that, right?
Be nice to see if you have to search for a new ISP, which one is good in your statistics. Yeah.
Yeah, so I wanted to show some stats across different service providers of outages. The problem is that we recently changed the algorithm of outage detection, and it would be a bit hard to compare before and after, but we will have that at some point. So this is just an example of an outage that happened at CenturyLink recently that actually impacted our service, and it was detected by our algorithm. So you see the timeline on top showing the end-to-end loss between our agents and one of our border routers. So we use CenturyLink as one of our providers. We have provided redundancy as well. But this was an interesting case because the BGP sessions between us and CenturyLink, they stay up. So from the point of view of BGP, everything was all in good. But in reality, we actually, our service was not available through some customers. So you see some packets being dropped there in the border. And then if you look at the outage, this is a new visualization we're working on. The way to look at this is you have on the right-hand side an aggregation of interfaces of endpoints belonging to ThousandEyes. So services at ThousandEyes.com. There's about 18 of them. And the numbers inside each circle are interfaces. So these are basically interfaces in the network group by autonomous system they belong to. And this gives you an idea about what's going on around the problem area when an outage happens, right? So it gives you that context. So in this case, you see CenturyLink there. There's the smoking gun almost in red. It's very clear. There's an issue there. On the routing side of things, we do something similar. So instead of active probing data, we use routing data. So we aggregate all the data from all the monitors over time. We look at events of prefixes appearing from routing tables close in time. So in this case, there's 2 routes in USA that get withdrawn. So we detect that as an outage event. And there's a root cause algorithm that works through the routing tables as well to pinpoint what's the most likely cause of or location of the outage in terms of network.
Looking at a routing, how does it do that? How do you do that?
At the high level, what we do is, so we see a population of prefixes appearing. We go back in time to the point where they were still available.
Yep.
And we see how the routers that saw those prefixes appear were reaching those prefixes. Mm-hmm. And there's usually a concentration around a certain service provider. For example, if all those prefixes are being routed through AS3, in this case, that's the most likely root cause.
Oh, that's interesting. Yeah, it's logical.
It's an inference. Obviously, the farther away,
it's an inference, sure.
The farther away you're from the origin, the less like is your root cause. So there's some tweaks, some adjustments we need to do there in the algorithm. So this is an example of an outage we detected using these detections. So this is a service provider in Russia. This was a big outage. We're talking about 150 prefixes almost. No, actually more. I have a number here. 638 there. You can see here, if you add up those two numbers, maybe I can zoom in a bit.
Mm-hmm. I can see it.
Okay. So it was a big outage in Russia. It impacted as well, destinations or prefixes in Ukraine as well, across that region. This is our BGP visualization. We know there was something wrong with that prefix. And by the purple dot there on top, that's the indicator we have for outages. So we know there was a routing outage happening at the same time. And and this is new routing visualization of outages. So this is where you can drill more into the outage. And what you can see here on the left-hand side are all the routers that we get BGP feeds from grouped by location. On the right-hand side, you see the prefixes being impacted by the outage grouped by network where they originated from. And again, the smoking gun there on that service provider, TRC Fjord, circle in red. So that was the autonomous system where that root cause basically finger pointed. In terms of Future capabilities that we're currently, so everything I talked so far is going to be available in the beta. But we are still working on other things that are going to be available after the beta, either at GA time or even after GA. We're also looking at routing Ajax and leaks. The distinction we do between Ajax and leaks is Ajax is when the origin ASN is the one announcing a prefix that belongs to someone else. Leaks is a case where there's actually a value violation. So the famous case of Amazon last year, where it started announcing customer routes to other customers, for example. So that's current work. We're also working on a way to detect when mitigation from a DOS service provider is happening, and this is actually not that hard to see from BGP. So there's only a certain number of DOS mitigation providers out there. You probably know Prolexic, and there's now part of Akamai. There's a bunch of others, VeriSign, and so on. So what we do, basically, we create a list of all these ASNs, and we look for patterns in BGP announcements that indicate when they start, mitigating some prefixes of some customer. And the other thing we're working on is the application outages. This one is more focused around critical applications or applications mostly used, most popular SaaS applications, business critical, to use our plethora of agents to detect when there's an application issue, basically. And if there's a network created by an outage, we can relate with all this information we collected so far here. And I think that's about it. You can create a free trial if you go to our site and play around with all this good stuff.
I think it's really interesting that you're continuing to develop the product in directions. So you're actually entering into adjacent markets here. So moving into route, like there's entire products, like I won't mention their names just to be courteous, but routing anomaly detection and then reaction to that, in the case of like hijacks and stuff, is actually products that other companies just dedicate themselves to, and you're just adding it on to what you're already doing, is the sense that I'm getting. And then obviously DDoS detection, again, same thing. You're scaling up from what you have into adjacent markets. Is that a fair comment? Yeah,
so I think the main theme is to detect any event that can impact a huge population of users. If there's hijacks or there can be other type of events. But I don't think it was intent necessarily to go in somebody else's market by any means, but it was more organic evolution of the product rather than anything else.
You've got access to the data more or less. Now you've just got to activate the
That's right.
function. Yeah.
Yeah, I see it also like this with the security aspects. You have this data and it's very user focused, but for the other use case, the data is also very relevant, to show that. I don't know how it looks in ThousandEyes. For example, one of the big botnet DDoS things that were ongoing last year, is especially interesting how...
That's good you mentioned, talking about Mirai botnet.
Okay.
That one. Yeah, that's good you mentioned that, because that was one event we did not detect with traffic outage detection because we were only filtering ISPs. And when in that case, when that happens, obviously Dyn was the one attacked the famous case service provider. It was DNS service provider. It was attacked denial of service because they're not an ISP. They're in the edge. Okay. We're not included. So what we did. What we changed after that was to include them, as well as a bunch of other critical service providers like CDNs and so on in our list. So if that happens again with Dyn, hopefully we'll detect it.
I'm pretty sure there will be another one of those.
That was a scary one.
You can go to the bank on that.
Yep. Thank you.
Thank you.
Thank you.